and it is based on rotation, rotational motion. Okay. So far we have seen linear motion, right? All the previous chapters had to do with linear motion. And we are going to talk on about rotational motion. Okay. So this is test next Monday. Okay, test next month, or exam, should put exam 2. Okay. So today we're going to talk about rotational motion, and this is based on chapter 12. Okay. So linear motion, we talked about position, change in position. Whereas, or also called displacement. And it is measured different units, right? Feet, meters, centimeters, and you can miles. You have a whole bunch of them. This is linear motion. In rotational motion, we have something similar. We talk of change in angular position. Okay, change in angular position, and or angular displacement, and it is measured in, okay, the units. One of them is obvious, degrees, right? So angles are measured in degrees. What else? So degrees, I'll just put DEG. Revolutions, REV. So degrees, revolution, and there's one more called radian, RADIAN, or RAD, radian. Okay. So rotational motion is measured in degrees, revolutions, radians, and just to give you an idea, 1 radian is approximately 57 degrees, right? Somewhere around that. 1 radian is close to 57 degrees. By the way we measure radians, okay, I'll come back here, right? So rotational motion, we generally take a circle of radius r, okay, and so, or let me use small r, and this distance, okay, we call s, or arc length, this, and angle in radians. So this is chapter 12. Okay, angle in radians and we use the Greek letter theta for angles, to represent angles. Okay, so this is theta. So angle in radians theta is equal to the arc length divided by the radius, which is arc length S, and the radius is R. Okay, so we can write rotational motion angle in radians is equal to S over R, right? And at around 57 degrees, S becomes equal to R at around, approximately around 57 degrees, S is equal to R. So if S is equal to R, then theta is equal to 1 radian. Okay? Because if these two numbers are equal, this and this, if you divide by the same number, you'll get 1. Okay, when S is equal to R. And that occurs at 57 degrees. What is the angle for a complete circle? Suppose you go completely around, right? We know for a complete circle, right? So I'm going to write that here. For a complete circle, 360 degrees. That is 360 degrees. Okay. The arc length is equal to 2 pi r, 2 pi times the radians. Okay. Arc length is equal to 2 pi r. So for a circle, okay, that is 360 degrees. S is 2 pi r, 2 pi r. And if you divide it by r, you get 2 pi, which, by the way, 2 pi is 3.14, okay? So that is 6.28 radians, RAD. Okay? In other words, 360 degrees is equal to 6.28 radians. So we measure angles in degrees in radians. By the way, 6.28 also is written as 2 pi, okay, radians. So if I can summarize all of this, 360 degrees is equal to 2 pi radians is equal to 360 degrees, 2 pi radians, which is 1 revolution. And angles also are measured in 1 revolution. A complete circle is 1 revolution. All right. So what about here? Half of this. What about 180 degrees? How many radians would that be? If I divide this by 2, it'll be pi radians, or half a revolution. Okay. What about 90 degrees? What about 90 degrees? If I divide this by 4, it'll be pi 2 radians, which would be 1/4 of a revolution. So all of these are different ways to go from one unit to another. So in summary, angles can be measured in degrees, radians, or revolution. Right? Okay, so let's go back here. Linear motion. We found linear velocity, which we call velocity v, which was change in position over change in time. For rotational motion, we have something similar. We call it angular or rotational velocity. Okay? Angular or rotational velocity. And we use the Greek letter omega. This is the lowercase omega. So angular or rotational velocity. The book uses rotational velocity. Some books use angular velocity. So we are going to use it interchangeably, but they mean the same thing. So angular velocity, the way it is defined, is change in angular position. Angular position divided by change in time. Which is written as, this is change in angle, right? Angular position divided by the change in time. Theta is the angle, change in position over change in time. Okay, so far so good. All right, let's go a step further. And so if, for example, right, you have a wheel, and let's say the initial angular position, remember this is, we're going to take east as 0 radians or 0 degrees or 0 at a revolution. So let's say the initial angular position, okay, theta I initial, okay, is let's say 2.1 or 1.2 radians. Okay, the initial angular position. And then the final angular position, right, it goes here. Okay. Is, let's say 5 minus, it's gone this way. Minus means it's gone this way. Minus 2.2 radians. Right? And this is at time t equals 0 seconds. And this, let's say this is at time t equals 5 seconds. Okay. So what is the angular or rotational velocity? Let's try to work that out. So angular or rotational velocity is equal to change in angular position divided by the change in time. Change in angular position, remember, is final angular position minus the initial angular position. Change in time. Okay, and let's put in the numbers here. The final occurred at 5 seconds. Let me use a different color. The final occurred at 5 seconds. And the position was minus 2.2 radians. So final minus the initial. The initial occurred at 0 seconds. And what was the position? Plus 1.2 radians. So what do you get? If I work this out, minus 2.2 minus 1.2 is minus 3.4 divided by 5 seconds. Okay, and if I divide that, I will get 0.68 minus 0.68 radians per second. Okay, so what has happened? It has gone from there to there. It has gone minus. We are going to take as anything moving clockwise is minus. So just remember that. Okay, so I'm going to write that here. Okay, clockwise in this class is negative, and counterclockwise is positive. So clockwise, so this is clockwise, so it's a negative. Now the book uses, to find directions, the book uses, remember these are vectors, okay? Change in position over change in time. We have to give it a direction. How do you give something that's turning a direction? We have a man-made rule, okay? We use our right hand. Most people in the world are right-handed. So that's a man-made convention. So if you curl your fingers, suppose this wheel is turning this way, right? If you curl your fingers in the direction of the turn, curl your fingers of your right hand, then the outstretched thumb gives you the direction. So in this case, the direction would be towards you, right? And that is positive because it's counterclockwise. Remember, counterclockwise is positive. So the direction for something that's angular velocity, okay, would be positive if it points towards you. If it goes clockwise, if you use your right hand and you curl it in the direction the wheel turns, then your outstretched thumb points into the whiteboard. And hence, the direction for clockwise revolution is that way. If you look in your book on page 2, by the way, I already did this, didn't I? This is not chapter 12. This was, I'm sorry, I'm going back to chapter 8. We already did this. That's my fault. All right. Guys, we did this. I'm thinking of a different class, and I'm behind there, and I forgot that we already did this in the last class. So I'm going to go, but anyway, we have already done this. All right, so I'm going to go to chapter 12. I'm sorry about this. That's my mistake. We have done this already. All right, so we're going to go to chapter 12. Because there's one more physical science class that I teach, and I know that I have to do, tomorrow I have to do that chapter. So chapter 12. Chapter 12, we are going to talk about, any questions, guys? All right, chapter 12. It's based on So chapter 12 is states of matter. States of matter. So matter is made up of atoms. And every atom is made up of a nucleus. So this is an atom. So an atom is made up of a nucleus, and which is positive nucleus, that is positive, okay, made up of positive protons and neutrons, neutral. They don't have a charge. Neutral neutrons. Okay. So a nucleus in an atom is made up of protons and neutrons, and then you also have one or more electrons going around. Okay. Electrons which are negative. And they obey certain rules, like charges repel. So if you bring a proton and another proton, they will repel. Okay. If you bring an electron which has a smaller mass than a proton, much smaller, the closer you bring them, the harder they repel. Okay. We call it an electrical force. But if you bring a proton and an electron, what happens is that they will be attracted to each other. The closer they come, the greater is the level of attraction, right? So that is the rule. So for example, the nucleus is positive because they are protons, and here you have electrons, and they are attracted to each other, and the electrons go around in an atom. So for example, if you look at the lightest element in the universe, which happens to be hydrogen. Hydrogen has one proton in the nucleus and one electron that goes around this hydrogen atom. So this is hydrogen. The next element in the universe, there's plenty of hydrogen in the universe. The universe, more or less 75% of the universe is made up of hydrogen. Plenty of it, right? It's the lightest element. The next lightest element in the universe is the helium atom. The helium atom contains two protons, which determine the characteristic of an atom. This has one, this has two protons. By the way, it also has two neutrons. Now, neutrons don't change. If you put an additional neutron, it still is the helium atom. It doesn't change its characteristics. So you have two protons and two neutrons in the nucleus. And because you have two protons, you have two electrons that go around. Okay? So this is a helium atom. And so on. The next element is going to have three protons. Then after that, four protons, 5, 6, and so on, right? So the number of protons keep going up, and the characteristic, the nature of the element changes, right? There's also plenty of helium in the universe, about nearly 20% or 24% is helium. But of course, on the Earth, we don't have, helium is neutral, we don't have a lot of it, right? So you have hydrogen, you have helium, and so on, right? So all matter is made up of atoms, and atoms can combine to form molecules. So all matter, right, is made up of elements, and elements can combine, is made up of atoms, and atoms can combine to form molecules. So atoms can combine to form molecules, right? So, for example, water is made up of 2 hydrogen atoms and 1 oxygen atom. So they combine. So you have 1 oxygen and you have 2 hydrogen joined together. Okay. So this is hydrogen, hydrogen, and this is oxygen. Right? So this is a water molecule. Okay, we are going to define density. Now, certain elements or certain matter is more dense than the other. Okay, so we are going to define density, and we're going to use the letter D. And density is equal to mass M divided by the volume V. So we write density is equal to mass over volume. Okay, how do we measure volume? For example, suppose you have a square container, right? This, I'm going to call it the length, I'm going to call this the width, and this the height. So volume of this container is length times the width times the height. So for example, if the length is, let's say, 2 meters, and the width is 3 meters, and the height, let's say, is 4 meters. What is the volume? What is the length? 2 times 3 meters times 4 meters. So 4 3s are 12 times 2 is 24. And it is M times M times M. So it is 24, 3 M's, right? By the way, we call this a cubic meter. So 24 cubic meters. That would be the volume of this container. If, for example, I just wanted to find the area. I wanted to find this area. Area is length times the width. So what is the area here? 2 times 3, 2 meters times 3 meters, which would be 6, and it is 2 M's multiplied together. We call this square meters. Square meters. So that would be the area. If it was feet, 2 feet by 3 feet, it would be 6 square feet. All right? So this would be the area of the bottom. So that's how you measure volumes. Um, for example, if you have a regular cylinder, then the volume of the cylinder, okay, is equal to area times the height. So if this is the height, and you know this area, then the volume of the cylinder is that area multiplied by the height, right? So the different formulas to find the volume. Okay. Any questions, guys? Okay. Let's go.
Yes.
Pardon? Okay. Let's go to the next step. So if I want to find the density, right? Suppose, for example, let's go back. I shouldn't have erased this. Okay. Suppose this is a container, length is 2 meters, width is 3 meters, and the height is 4 meters. Not drawn to scale, right? And if I pour in a mass of, I pour 24,000 kilograms of water, H2O, okay? So pour 24,000 kilograms, and when you do that, you will find it will fill to the brim, right? And so the mass, so what is the density? The density is 24,000 kilograms divided by the volume. So the volume is 3 times 2 is 6, 6 times 4 is 24. So the volume is 24 cubic meters. All right, so 24 and 24 cancels off, so you get 1,000 kilograms per cubic meter. So, and this is the density of water. Okay, the density of water is 1,000 kilograms per cubic meter. If I want to convert it into grams, sometimes the units are written as grams per cubic centimeter. What if I want to convert it from 1,000 kilograms per cubic meter to grams per cubic centimeter? All right, so let's try to figure that out. All right, so let me write this on top. Okay, so the density of water, so I'm going to write it here, is 1,000 kilograms per cubic meter, and I'm going to write it this way. Cubic meter is m meter times meter times meter, right? So that's the density of water. Okay. Now a kilogram, by the way, a kilogram, 1 kilogram is 1,000 grams. So if I replace this kilogram by, I'm going to replace it by 1,000 grams. This is grams. And each meter is 100 centimeters. So this is 100 centimeters. This is 100 centimeters. And this is 100 centimeters. Right? So what do you have? Density of water, 1,000 times 1,000 is 1,000,000. So 1,000,000 grams. Right? What about meter times meter? So you have 100 times 100 times 100. So 100 times 100 times 100, that's 6 zeros. So you get 1,000,000 6 zeros, right? 2, 4, 6. And each is centimeters times centimeters times centimeters. That's cubic centimeters. Okay. So I've replaced the kilogram with 3 zeros, 1,000, and each of these meters is 100 centimeters. So you have a million, 1 and 6 zeros. A million divided by a million is 1. So we can also write the density of water is 1 gram per cubic centimeter. Okay, 1 gram per cubic centimeter. That is the density of water. All right. So 2 ways of writing the density of water. So density of water, okay, is 1,000 kilograms per cubic meter, or in units of grams, it's 1 gram per cubic centimeter. Anything that has a density greater than 1,000 kilograms per cubic meter will sink in water. Anything that has a density less than 1,000 kilograms per cubic meter will float in water, right? So if you go to chapter 12 on page 242, turn the page to 242, table 12.1. Okay, so this is chapter 12, page 242, table 12.1. You'll find all the densities of different substances are given there. Okay, for example, they have said density of ice, which is solid water, is it is 0.92 grams per cubic centimeter. It's less than 1. That's why ice floats in water, because the density of ice is less than water, which is 1. This is 0.92, and that is 1. If I want to convert it, right, how do you go from grams per cubic centimeter to kilograms per cubic meter? What do? You multiply it by 1,000, right? If I multiply this by 1,000, I'll get that. So if I multiply this, grams per cubic centimeter, by 1,000, I'll get 920 kilograms per cubic meter, right? So that's how you convert from one unit of density to the other. Let's take another example on page 242. Let's look at magnesium. Okay, the density of magnesium, or manganese, magnesium, is 1.75. So density of magnesium. By the way, the symbol for magnesium is Mg. Okay, density of magnesium is 1.75 grams per cubic centimeter. If I want to convert it into kilograms per cubic meter, I would have to multiply it by 1,000. So if I multiply this by 1,000, okay, the density of magnesium in kilograms would be 1,750 kilograms per cubic meter. Right? So that's how you convert from one unit to the other. Right? So that's how you decide. Also, remember the formula density is equal to mass over volume. All right. If you want to memorize it, you can figure out. Suppose your So density, remember our friend, the triangle, density is equal to mass over volume, right? If I want to find the mass, then it will be density times the volume. If I want to find the volume, you cover the volume, it will be mass divided by density, right? So if you know one way, if you know this, D is equal to M over V, and you can figure out how to do the other, how to find the mass and the volume. So if you're given the density and you know the volume, then you can find the mass. Okay, so the next thing we are going to define, matter can exist in 4 different ways. Okay, matter has 4 different, we call them phases, depending on the temperature. So at the lowest temperature, all materials, most materials, 99.9% of the materials are solids. Okay, so this is at the smallest temperature. So this is temperature. Okay, so this is the lowest temperature. I'll put small t, right? As you raise the temperature, for example, if this was ice, if you raise the temperature and if you reached a temperature of 0 Celsius or 32 degrees Fahrenheit or 273 degrees Kelvin, this will turn into a liquid. So the next phase, okay, is a liquid. So this is a solid. This is a liquid. And this will be at a higher temperature than this. So the temperature is increasing, okay, in that direction. So this is increasing temperature, all right? Now, if you take the temperature even higher, for example, water, if you take it to 100 degrees Celsius or 373 degrees Kelvin or 212 degrees Fahrenheit, water changes into a different, it becomes a gas. Here, the gas molecules are far apart compared to their size. Okay, so this is a gas. So this would be at a higher temperature. In the case of water, we call this ice, we call this water, and we call this steam. But they all have the same formula, H2O, 2 hydrogen atoms with 1 oxygen atom. And if you raise the temperature even higher, at a certain point, this gas, these atoms and molecules will begin to pull apart. Okay, the electrons will be pulled apart, and it turns into a phase called plasma. All right, so it's very bright. So this is plasma, and this occurs at a real high temperature. So as you increase the temperature, it goes from a solid, it melts and becomes a liquid, and then it boils and becomes a gas. And then further, if you heat the gas to a real high temperature, okay, nearly 2000 Kelvin, it begins to, the electrons begin to separate, right? And it becomes a plasma. So there are 4 states, 4 different phases of matter. If you take aluminum at 0 degrees Celsius, aluminum at 660 degrees Celsius, remember water melts at 100 degrees Celsius. Water melts at 100 degrees Celsius. Aluminum will melt at 660 degrees Celsius. And then even at a much higher temperature, it will become a gas, right? So all matter can be in any of the 4 different phases depending on the temperature. You may have seen plasma, for example, if you have ever seen a welder weld, right? When a welder welds, you can see that it gets really bright. That's because the gas has turned to a plasma. Okay. The next thing we are going to talk in this chapter is pressure. So what exactly is pressure? So pressure, the way we define pressure, pressure, P. So pressure P is force divided by the area. F over A. So pressure, we use an uppercase P. Remember, we used a lowercase p for momentum. For pressure, we use an uppercase P, and this is equal to force over the area. And of course, if I want to find the force or the area instead, if you're given the pressure and area, how do you find the force? Well, pressure is equal to force over area, and if I want to find the force, it becomes pressure times the area. If I want to find the area, it becomes force divided by the pressure. Okay. Let me give you an example. Suppose you have an object that has a weight of say 200 newtons, okay, and the area here, the area is 10 square meters. So you see, so what is the pressure at the bottom? What is the pressure at the bottom? Okay, so the pressure is equal to force over area. So what is the force? The force is the weight, 200 newtons. That's the total weight of that object impresses itself on the bottom area. And the area is 10 square meters. Of course, 200 divided by 10 is 20 newtons for every square meter. So every square meter of this bottom would feel a weight of 20 newtons. Okay, it's 20 newtons per square meter. So if I were to write this out, okay, 20 newtons per square meter, so pressure is equal to 20 newtons for every square meter, and we define 1 newton for every square meter. We call it 1 Pascal of pressure, which by the way we write it as PA. Okay. We abbreviate it as PA. So what is this pressure? This pressure would be 20 pascals. 20 PA, pascals. So pressure is measured in pascals. All right. Okay, let's go to the next. All right, so for example, let's go back to our original, right? We had this. Okay, this, I believe, the length was 2 meters, the width was 3 meters, and the height was 4 meters, and we filled it with 24,000 kilograms of water, and we found the density, right? So let's go back. We found the volume. Let's start with the area. We found the area at the bottom, which was what? 3 times 2, 3 meters, length times the width, or width times the length. Okay. We found the volume. And the volume was length times the width times the height, which was 2 meters times 3 meters. So I'm just recapping what we did, which is 24 cubic meters of volume. Right? And then we found the density. The density of water is 1,000. Okay, so the density of is 1 gram per cubic centimeter, and we found that the density was 1,000 kilograms per cubic meter. Okay, so you can convert from here to here by multiplying this number by 1,000, and you get that, right? And so area times the area, volume, mass. Mass is 24, right? You can actually find it from the density. Remember, density is equal to mass over volume, right? Let me write it here, right? So if I put that triangle, this is density is equal to mass over volume. If I know the density and I know the volume, I can find the mass, right? In this case, the density is what? 1,000 kilograms per cubic meter, right? And the volume is 24 cubic meters, right? So if you were to work this out, this would become 24,000 kilograms. Okay, cubic meters and cubic meters will cancel out. Okay, how do you find the weight? Suppose I want to find the pressure at the bottom of this tank filled with water. Suppose I want to find what is the pressure at the bottom, right? In order to do that, I need two numbers. Remember, to find the pressure, I need the force, which is the weight in this case, and the area, which I already have. I have that area. So to find the pressure at the bottom of this tank containing this water, I want to find what is the pressure at the depth of 4 meters. Or if you were swimming in this tank, right, at a depth of 4 meters, what would be the pressure, right? So the pressure, let's find the force. The force is the weight. So the weight is mass times gravity. The mass here is 24,000 kilograms, and gravity is 9.8, but I'll take it as 10 meters. In the exam, if you're given this problem, you can take it as 10 meters per second squared. Right? So what is the weight? 24,000 times 10 is 240,000 newtons, kilograms times square meters. So that would be the weight. So this is the weight that would be felt at the bottom here. So what is the pressure? The pressure at the bottom, which is force over area, would be what? The force is the weight, which is 240,000 newtons, and the area at the bottom is 6 square meters. Okay, and if you divide 240,000 by 6, you get 40,000 newtons per square meter. That would be the pressure, which, by the way, we call 40,000 pascals, right? Because pressure is measured in pascals, right? Suppose, let's see if you can try one. Let's see if you can try one at home. Suppose the density, you're given this. In the exam, you'll be asked to find all these quantities, right? Suppose you're given the density of, let's say, aluminum. Okay, suppose this is a block of aluminum, and you'll be given this diagram. Let's say this is 0.3 meters, 0.5 meters, and the height is, let's take the height. So this is 0.5, okay, and the height is 0.2 meters. That's the height. and this is aluminum, okay, not aluminum, yeah, let's take aluminum. Aluminum, the symbol is Al, the symbol for aluminum, and if you go to page 242, the density of aluminum is 2.70. So the density of aluminum is 2.70 grams per cubic centimeter. So you'll be given this in the exam. You'll be asked to find the area, the volume, the mass, the weight. Okay, so you'll be asked to find the weight and hence the pressure at the bottom. So after all of this, you'll be asked to find what is the pressure at the bottom here. What is the pressure, right? So see if you can do this. So I'll give you a few minutes. See if you can find, you know the dimensions, right? The area would be 0.3 times 0.5. Right? And then the volume would be that times 0.2. Okay. See if you can do that. All right. Again, this is pressure, by the way. Pressure. So convert this into kilograms per cubic meter first. And once you have converted it, then see if you can come with the answer. See if you can do that.
Is area length times width?
Yes, area is length times the width.
And then volume would be length times width times
The
height,
height.
right? All three together?
Right. Which is 0.2.
Okay.
And mass, to find the mass, right? Once you have converted this into kilograms per cubic meter, you're going to multiply it. It's density times the volume. Right? So mass would be that, density times the volume.
That says 0.3.
Yeah, this is 0.3 meters. This is 0.5.
Okay.
And this is 0.2. Okay, so if I want to convert this into kilograms per cubic meter, I have to multiply this by 1,000. So the answer here, let me put this in red. The answer here would be, the density would be 2,700 kilograms per cubic meter. So if I multiply by 1,000, remember I had done that earlier, right? Area, which is the length times the width, which is 0.3 times 0.5, which would be 0.15 square meters. Make sure you put the correct units, all right? I sometimes take off points for that. Okay, so 0.3 times 0.5, right? And then if you multiply this by 0.2, right, it would be 0.030, okay, cubic meters. Okay, and then what is the mass? Mass is density times the volume. So this is density times the volume. And we know the density, which is 2,700 kilograms per cubic meter, and the volume. The volume is 0.0. So if I multiply this by 0.03 cubic meters, so that and that will cancel off, and 2,700 times 0.03, 2,700 times 0.03, and so you get 81 kilograms. So it would have a mass of 81 kilograms. And what would be the weight of this block? And what would be the weight over the area? So The weight of the block is mass times gravity, which by the way is 81 kilograms, times gravity is 10 meters per second squared. So this would be 810 newtons. That would be the weight. And the pressure would be the weight, which is 810 newtons, divided by 0.3, the area, which is 0.15 square meters. Okay, so if I divide 810 divided by 0.15, I get 5400. So this is 5400 newtons per square meter, which of course is 5400 pascals, and that would be the answer, the final answer. Okay, 5400 pascals. Okay. So you may get one of the problems based on this, all right? So, and you would have to know how to do it because it incorporates density and pressure. Okay, let's talk a little more about pressure, right? What we find regarding pressure, I'm going to so we call the sea level, right? And as you go up a mountain, so suppose there's a mountain, so pressure at sea level, okay, so pressure at sea level, that's there. Pressure at sea level is, we find it's approximately, it's 101,300 pascals, okay, which for this class we are going to approximate this as 100,000 pascals. Now where does that pressure come from, right? If you look at the atmosphere, right, and if you could calculate the pressure, remember the air above, so if you're standing at sea level, right, the air above you has a weight. It pushes down on you, right? And the pressure is 100,000 newtons. Pascal is newtons for every 1 square meter. Okay, 1 square meter. Now I have shown you, 1 square meter is about from there to there, right? From there to there, that's 1 square meter. All right. Oh, I'm sorry, 1 meter. That's 1 meter. If you stretch your arm out. All right. So think of a square, 1 square meter. So the atmosphere has a weight of 100.
Are you measuring the meter from the whiteboard? Is it the whiteboard? What do you
No,
do with your arm?
yeah, with my arm out, right?
Yeah,
So
your arm.
yeah, it would be from there.
From your elbow to your
Yeah,
wrist?
no, from here to here, shoulder. That would be
Oh,
about
shoulder.
okay.
Okay. That's 1 meter?
Yeah, that would be a meter.
Okay.
If you stretch your arm out from the end here to your shoulder is approximately 1 meter. So that,
But what if my arms are shorter?
yeah, that's, but approximately humans, like, they come close to that. I know what you're saying. There'll be variations.
So it's not like, okay. Okay, got
So,
it.
that's why we have the meter stick to standardize it, right? Remember, in the
Got
first
it.
class, I said they used to measure cloth, right? They used to, in France, they would measure cloth per square meter, per meter length, right? They would
Okay.
take the cloth from there to there, and that would be 1 meter. And then they would fold it, and that you would have 2 meters of cloth and 3 meters. That was approximate, right? And then people, used to get cheated because some guys had shorter arms, some guys had longer arms, right? But 1
Okay.
square meter. So every square meter of your body would feel a force of 100,000 newtons. Okay, 1 Newton is about the weight of a hamburger, small hamburger. Okay, 1 Newton. So think of every square meter of your body would feel a weight of 100,000 newtons. That's a lot of weight. If you look at the skin, the total skin, humans, the total skin is approximately 2 square meters in area. 2 square meters. So your body, right, on all sides has a total weight of 200,000 hamburgers, newtons. So the question is, from that total weight of the air, right, why don't we collapse? Well, it has to do with the pressure inside your body. So if I may draw it here, right? So this is you, right? So there is a pressure for every square meter of 100,000 newtons per square meter, 100,000 pascals, which, by the way, in pounds per square inch, this is 14.7 pounds for every square inch. So every square inch of your body feels a weight of 14.7 pounds. That's quite a lot of weight, every square inch, right? So why doesn't your chest collapse under this pressure? That's because of things, you inhale air, etc. The internal pressure from the inside is also 100,000 pascals. Okay, approximately 100,000 pascals or 14.7 pounds per square inch. That's why your body doesn't collapse. Okay, there's an equal pressure inside, right? So this is the pressure at sea level. By the way, sometimes we call this 1 atmosphere. That's another way of gauging pressure. Or 1 ATM, 1 atmosphere, right? So different units. They also write it as 760 millimeters of mercury, Hg, okay, mercury. And I'll explain why. In other words, this pressure will support this amount of mercury, this length of mercury, okay, in a tube called a barometer. So sometimes they say the pressure is 760 millimeters of mercury. If the pressure drops to half an atmosphere becomes half, this would be half of that, okay, which would be 355, right? 355 or 385. Okay, 760. Okay, 760. 380. I'm sorry, 380. 380. Half the pressure. So these are different units that they use. The people who give the weather reports, they generally use this unit. Right? In physics, we tend to use this unit, which is approximately, we use the approximation sometimes, 100,000 pascals or 100,000 newtons. Now here's something that you should know. As you climb up a mountain, the pressure drops. By how much? The pressure for every, so as you climb up a mountain, so this is at sea level, for every 5,500 meters, 5,500 meters, which is approximately 18,000 feet, the pressure becomes half. So if the pressure here is 100,000 pascals, okay, if you climb up this height, 18,000 feet, this pressure will drop to half. it'll become 50,000 pascals, right? That's because there's less air above you. Remember, the air goes up a certain distance and then it kind of gets very thin. Yep.
You started off at what, 150,000? What does that say?
Yeah,
At the
50,000
at the
pascals.
bottom is 150, and then at
No,
like
no. Here it
after
is here it is 100,000. So this
uh-huh.
is 100,000, and then if you go up,
Yep.
climb a height of 18,000 feet, it will drop to half.
Okay.
So if you go up another,
And then if you go another 18,000, it's just gonna go to zero then, huh?
no, it'll drop to
Zero
half of that.
pressure.
Yeah. So it'll become 25,000
Oh,
pascals.
25,000. Oh, okay. So it only cuts off half. Okay, get it.
Right, right. Every 18,000 feet, it drops by half. Okay, approximately 5,500. So this total 5,500 plus 5,500 is 11,000 meters, which is 36,000 feet. By the way, 36,000 feet is where airplanes fly. All right. So if the airplanes weren't pressurized, right, you would immediately, at this height, the pressure is 1/4 of what it is at sea level, and you would immediately lose consciousness at that height if the cabin wasn't pressurized. So before airplanes take off, they pressurize the cabins to make sure that you don't, um, you don't pass out. All right, and there's a reason for it.
Is that why our ears pop?
Yep, as you go up, your ears pop because they pressurize it here. Okay,
How
and
much pressure can an earlobe take?
um, how much you mean? Your body definitely at this, you may survive here, but here you would pass out completely. Why? Because your body, right, needs oxygen, um, and oxygen is forced into your bloodstream by pressure. Okay, so they put pressure, and that pressure forces the oxygen into the bloodstream. All right, so here the pressure is 100,000, so that forces, so when you take in air, breathe in air, that pressure forces that air or that oxygen into your bloodstream. Here the pressure is very low, so the amount of your blood in your lungs cannot get oxygenated, right? So you begin to pass out, because once your brain is starved of oxygen, you pass out, right? So the pressure drops by 25,000. So that's why they pressurize the cabin, so that, you know, the pressure inside the cabin is about 100,000 pascals, right? Also, if you go down, for every, so this is water. So for every 10 meters, okay, now this is not drawn to scale. This is 5,500 meters. This is 10 meters. So it's not drawn to scale. For every 10 meters, the pressure due to the water increases by 100,000. So here, the pressure due to water alone, pressure from water, is about 100,000 pascals, right? What is the total pressure? The pressure due to the atmosphere and the water, the total pressure is 200,000, right? 100,000 from the atmosphere, and then another 100,000 from the water, so 200,000. If you go to a depth of another 10 meters, total of 20 meters, the pressure from the water will now be approximately 200,000, right? Because 20 meters of water. And what is the total pressure from the atmosphere plus the water? Would be 300,000 pascals. Okay. The pressure due to water alone, sometimes we call it gauge pressure, right? Okay, gauge pressure is the difference between the total pressure, right, and uh, the total pressure and the pressure at that point. So if the total pressure is 100,000 pascals minus the 100,000, that would be the pressure at it would be 100,000 pascals. Okay, so gauge pressure. So for every 10 meters that you go down, suppose you're swimming here, for every 10 meters, okay, you would feel a pressure from the water of 100,000 pascals, plus the air pressure. But of course, the air pressure inside your body is neutralized, right? Now we can figure out why the pressure is, okay. So one of the problems I'm going to give you to do at home and then email me is to find the pressure at a depth of 10 meters, right? I'll show you how to do that. What we're going to find, we're going to talk of something called a barometer, right? In particular, we start off with a simple barometer called a water barometer. A barometer is used to measure pressure. So barometer is used to measure pressure, right? A simple barometer is a water barometer. So if I take a tube, right? Let's say it's an 11-meter tube. Now this would be impractical because think of something that is 11 meters long. That would be pretty large. But you get an idea of how, it's simple enough that you will understand how it works. So if I fill it with water to the brim, right? And then I take this barometer, close it so that the water doesn't spill out, and turn it and put it in a tank filled with water, right? So here's a basin filled with water, okay? And this is filled with water, okay? I put this barometer in this. So this is filled with water, and I turn this completely around, right? And so this is the barometer, right? Filled with water. And what I find is that the water will go down. And when it has dropped, when this height is 10 meters, so the water will empty itself and stop when it reaches a height of 10 meters. So this is water, right? And why is that? Because remember 10 meters of water, right? What is the pressure here? A column of, the pressure here is 0 because the water has gone out. The pressure is approximately 0 pascals. Okay. What is the pressure due to 10 meters of water? What did we say? The pressure here is what? 100,000 pascals, or 14.7 pounds per square inch, right? The water. The pressure here, the pressure from the weight of the water, 10 meters of water. And what is the pressure outside? The pressure outside due to the atmosphere, what did I say? is approximately 100,000 pascals, or 14.7 pounds per square inch. And so they balance each other. Can you see that? They balance each other. See, the pressure here is 100,000 pascals. The pressure due to the atmosphere is 100,000 pascals. So it's like a balance. They balance each other and it remains steady. Okay. What happens if I could physically carry this? This would be impractical, but if I could physically carry it up a mountain. So suppose I go up a mountain, you will find that the pressure drops, right? Suppose you go up a mountain, and what is the pressure outside? The pressure outside is 50,000 pascals, which is what? Half of that, 7.35 pounds per square inch. So the pressure outside has dropped. It has become half. Okay. What do you think will happen to the water? Because the pressure here is greater, the water will be forced down. And the water will empty itself until it reaches what height? What height will the water reach? So if this is 10 meters,
I mean,
the water will reach a height of 5 meters, right? 5 meters will give 50,000 pascals inside. See, 10 meters gave 100,000, 5 meters will give 50,000, and the water will empty itself until it reaches a height of 5 meters. So it will balance the outside pressure. These two will be balanced. Okay. Suppose I go even higher, right? I go to a height of 36,000 feet. What is the pressure outside? The pressure outside is now 25,000 pascals. So what do you think will happen to the water? The water will drop to what height? 2.5 meters, right? So the height of the water column will be 2.5 meters, because now 2.5 meters will give you what? 25,000 pascals of pressure. And the outside pressure is 25,000 pascals. So in a simple water barometer, by noting the height, I can tell the pressure. If the water level is here at 2.5 meters, the pressure outside is what? 25,000 pascals. If the water level is at 5 meters, the pressure outside is 50,000 pascals. If the water level is at 10 meters, the pressure outside is approximately 100,000 pascals, right? So that's how we find the pressure. But of course, remember, something that's 10 meters long, right? That's 10 arm lengths. That would be impractical. So instead of water, we use mercury. Mercury has a density of water is 1 gram per cubic centimeter. Compared to that, density of mercury, Hg, mercury is a liquid, so I can use it in the barometer. But the density of mercury is 13.6 grams per cubic centimeter. It's 13.6 times massive, has more mass, and hence more weight than water. So I'll need 13.6 times less. So instead of using 10 meters, if I divide 10 meters by 13.6, this will give you approximately 7.6 meters, which in millimeters is 760 millimeters. So instead of having this, we use what we call a mercury barometer. So a mercury barometer is a slim tube filled with mercury, and when the outside pressure, so this is mercury, Hg, when the outside pressure is 100,000 pascals, or 14.7 pounds per square inch. Okay. The mercury barometer will be at a height of 780, I think it's 760 millimeters. Okay. What happens when the pressure outside, you go up a mountain and the pressure drops to 50,000 pascals, or half of 14.7, 7.35? What will happen? The level of mercury will go to 380 millimeters. Okay, it'll drop. So by noting the level of mercury, I can tell the pressure outside. If it's 380, the pressure outside is 50,000 or 7.35 pounds per square inch, every square inch. If it is 760, the pressure outside is 100,000 pascals, right? Or 14.7 pounds per square inch. Okay, guys, let's complete this chapter. And so we're going to talk about how sink or float, right? So we're going to talk about Archimedes' principle. So Archimedes' principle states that the buoyant force is equal to the weight of the displaced fluid. So Archimedes' principle states that the buoyant force is equal to the weight of the displaced fluid. So for example, if your body displaces, you get in a swimming pool, right? And let's say there's a kid in the swimming pool, right? And this is the kid there, that's the swimming pool, he's floating in it, right? And the amount of water that is pushed aside is equal to the volume of this person, right? So whatever volume he has, that amount of water will be pushed aside. So for example, suppose this person, his weight in air, suppose you have this guy, his weight in air is, say, it's a kid, let's say it's 100 pounds, okay? And his body pushes aside, the amount of water that is pushed aside, that's the amount of water that is pushed aside, okay, has a weight of, so weight of the water displaced or liquid displaced, this is weight of the water displaced, is 10 pounds, okay? Then the upward force that he feels will be 10 pounds. So if his body displaces 10 pounds of water, he will feel 10 pounds lighter because there's an upward force that is equal to 10 pounds. If his body displaces 15 pounds of water, okay, there'll be an upward force of 15 pounds. Okay, and so he'll feel 15 pounds lighter. So what is his weight in water? So in this case, if his body pushes aside 10 pounds of water, his weight in water would be what? 90 pounds, right? Because the buoyant force, which is the weight of the displaced fluid, is what? 10 pounds. So the upward force or the buoyant force, this is the upward force, will also be 10 pounds. Okay. Suppose I push him in deeper, right? So that, say, his head and the remaining portion of his body is underwater. So now, right, this amount of water is displaced. And let's say the amount of water pushed aside is 30 pounds. So if you could find his weight in water, what would that be? Be 70 pounds, because there's an upward force of 30 pounds. And according to Archimedes, the amount of upward force depends on the amount of water displaced. So the upward force in this case, or the buoyant force, will be 30 pounds. All right. So that is Archimedes' principle. How does that help in flotation? Okay. So for example, suppose you have an object in water. Okay. I push it underwater. Let's say the weight of the object is 70 newtons. So weight, I'll call this weight in air or weight, okay, 70 newtons. I push it underwater. What will the object do? It will begin to rise, right? It will float in such a way that the amount of water it pushes aside, this is the amount of water it pushes aside, is 70 pounds. So when it pushes aside 70 pounds of water, there will be an upward force of 70 pounds, right? Which will balance the weight of 70 pounds. And therefore, what's the net force? What's the net, by the way, this is newtons. I mistakenly called it, okay? So what is the net force? What is the weight in water? Anyone?
It should be 0, right?
Right? It'll be 0, right? So what happens is that the object will rise and it will stop when the amount of water that has pushed aside is exactly equal to its weight, right? So the weight of the water displaced. So this is the weight in air. So it rises until it pushes aside 70 pounds of water. This is weight of the water displaced. And therefore the weight in water now is 0 pounds, 0 newtons, and it floats. So that is the principle of flotation. Now the question is, why is the upward force equal to the weight of the water displaced? So let's try to reason that out. So the question is, why is the upward force equal to the weight of the water displaced? Why is the buoyant force equal to the weight of the water displaced? So what happens here, suppose you have this amount of water, right? And let's say the weight of the water was this. I just take a portion of the water, okay? And let's say the weight of the water, if you could weigh that water take it outside and weigh it, okay? Let's say is, uh, yeah, let's say 100 newtons, okay? So this water this is a tank of water, but just this portion of water, let's say weighs 100 newtons. How much water has it pushed aside, right? Because this weight is 100 newtons, and it is, remember, it's neutrally buoyant. In other words, it doesn't come up, it's just there. That means the upward force has to be what? Weight of the water pushed aside, which is the upward force, has to be 100 newtons. That's why that column of water doesn't go down or go up. Okay, so it pushes aside 100 newtons of water. That's why the water remains stationary inside. Okay. Now what happens if I take this object, if I could take that water and replace it with an object, let's say it's made out of metal and it weighs 180 newtons. Okay, so it has the exact shape. So I take that water out. If I could magically take that water out and replace it with this metal, which has a weight in air of 180 newtons. So this is some metal. I take it and I place it exactly in that spot. It has the same volume, right? Now, what is the weight in air? The weight in air is 180 newtons. But the amount of water that has pushed aside was the same amount of water that you removed, right? What was the weight of the water? The weight of the water is 100 newtons. Weight of the water displaced is 100 newtons. So what is its weight in water? Its weight in water is 80 newtons, right? So can you see that even though it has a weight of 180 newtons, by pushing aside 100 newtons of water, there's an upward force of 100 newtons. Before the water was pushed aside, can you see the surroundings supported 100 newtons of weight? Okay. If you put anything in its place, if you remove that water and put anything in its place, the surroundings haven't changed. The surroundings will still support 100 newtons of whatever you put in there. Right? Suppose this object had a weight of, say, 220 newtons. It has the same shape. So I take this out, I place it with that. Now this is 220 newtons, right? The surroundings haven't changed. Before I placed this object here, the surroundings supported what? 100 newtons of water. So the amount of water that was here was 100 newtons before I placed it with that object. So the surroundings haven't changed. The surroundings will still support 100 newtons of whatever you place in there. So it will support 100 newtons, leaving how much unsupported? 120 newtons of weight is unsupported. So its weight in water is 120 newtons. Right? So why is this important? This is called the principle of flotation. When things float, the upward force, when things float, the upward force, which is the weight of the water displaced, is exactly equal to the weight in air, weight of the object. So I'm going to write when things float. Now it could be water, it could be mercury, it could be any liquid. When things float, okay, the weight of the water liquid displaced is exactly equal to the weight of the object. That's why you have flotation, right? So weight, so when it floats, this is the amount of water that is displaced, and that weight, the weight of the water pushed aside, is exactly equal to the weight of the object. If the amount of water pushed aside is greater, okay, the object will have to go higher for it to be balanced. Okay, if the weight, if the amount of water pushed aside is less than the weight of the object, what will happen? The object will sink. Okay? If the amount of water displaced is greater than the weight of the object, what will the object do? The object will rise and it will stop when the weight of the water or the liquid displaced is exactly equal to the weight of the object, right? So we call this the principle of flotation. Now, the reason why it's called Archimedes' principle is the story goes that there was a king and he had a gold ingot. A piece of gold, I-N-G-O-T, ingot. By the way, gold, the symbol is Ag. Okay, I think it's Ag. Okay. I always confuse myself because I know silver is AU, I believe. Okay. It doesn't tell me. Okay. Anyway, so a gold ingot, and he wanted this jeweler to fashion a crown. So the jeweler made a crown, okay, and he gave it to the king. So let's say this weighed 100 newtons in the air. This also weighed 100 newtons. But the king got suspicious. He thought that guy probably mixed gold with copper. All right, and kept part of the gold for himself. So he asked Archimedes, is there a way to find out, if I've been tricked? After all, both weigh the same. So how do you tell if he has replaced some of the gold with copper? So Archimedes thought about it. He was sitting one day in his bathtub and realized he came across the solution. He figured out how to tell if it was true. And all he did was he took an actual piece of gold and weighed it in water, right? So it will have a certain weight in water. What happens if you put some other foreign material? Suppose in those days aluminum wasn't invented, but suppose he made a gold. Suppose there was aluminum, right? Aluminum has a very small density, so compared to other metals. So can you see he would need a lot more aluminum to get 100 newtons, right? Suppose he made a crown of aluminum and painted it with gold and gave it to the king. Can you see if you put it in water, what will happen? It will push aside a lot more water, okay? Because you need a lot more volume of aluminum to get 100 newtons. So it will push aside a lot more water, and therefore the upward force is going to be greater in water, right? So for example, let's say here the weight in air is 100 newtons, and let's say it pushes aside 20 newtons of water. So weight of the water pushed aside is 20 newtons. So what is the weight of this? This would be 80 newtons, right? The weight in water. What if you take this aluminum crown and put it in water? Right? Now, to get the same weight, 100 newtons, you would need a lot bigger piece of aluminum. And hence it will push aside a lot more water. Bigger aluminum means, I'm talking of volume. So what would that be? Let's say it is 40 newtons. Okay, now it has more volume of water that it's pushed aside. So here the weight in air is 100 newtons, and the weight of the water displaced is now a lot more, 40 newtons. So what is the weight in water? The weight in water will now be 60 newtons compared to 80 newtons. So in the air, they both weigh 100 newtons. But the moment you put it in water, right, if it has any foreign material, it will push aside a different amount of water, and therefore it will have a different weight. Does that make sense? So even though they have the same weight in air, the moment you put it in water, because they are made out of different material, they will push aside different amounts of water, and therefore the weight in water will be different, right? If here the weight of the water pushed aside is 20 newtons, the upward force will be 20 newtons, and therefore there'll be a downward force, that's the weight in water, of 80 newtons. Let's say aluminum pushes aside a lot more water because you need a lot more aluminum to get 100 newtons. Let's say the amount of water pushed aside is 40 newtons, and therefore it is going to weigh 60 newtons. So they will have different weights in water. And the story goes that's what Archimedes did. He took a pure piece of gold that had the same weight. They had the same weight in air, right? Pure, this was 100 newtons. So he took a pure piece of gold that was 100 newtons, and he found the weight in water of both. And he found that this had a smaller weight in water. And the story goes, the jeweler lost his head. Okay, now we don't know if the story is true, but it's kind of an interesting story. It brings out Archimedes' principle and the principle of flotation. All right, and the last thing we are going to do in this chapter is called Bernoulli's effect. Right? So we're going to do Bernoulli's effect. Bernoulli's effect. So what exactly is Bernoulli's effect? Okay, so Bernoulli's effect states that the pressure in a fluid decreases as its velocity increases. The pressure in a fluid decreases. It decreases as its velocity increases. As its velocity increases. So if the liquid is flowing or fluid is flowing faster, the pressure, the inside pressure, actually decreases. If it's flowing slower, okay, the pressure increases. Okay, so let's see what that is. All right, so that's Bernoulli's effect. So anytime the fluid flows faster, the pressure decreases. Right? So let's take a pipe, and let's say the pipe, so there's water flowing through this pipe, and the pipe narrows. Okay? And then again it gets larger. So the pipe narrows. Okay, and what we find is that when the pipe narrows, the speed of this liquid increases. In other words, suppose the amount of water that's flowing every second is about a gallon, right? So let's say gallon is a volume, right? So let's say the volume per second, let's say 1 gallon of water flows per second, right? So this is 1 gallon of water. Let me use a different color, right? Let's say that's 1 gallon. Okay, 1 gallon per second. So in 1 second, the liquid goes from here to here. This edge, right, comes over here in 1 second. Now what about here? A gallon of water, that's 1 gallon, right? Same volume. So that's 1 gallon. Can you see that how much water is flowing? The amount of water that has to flow through the narrow part should also be 1 gallon per second. Otherwise, the water will, the pressure will build up, right? So the same amount of water every second has to flow through. Can you see here it has to go faster? Do you know why? Because this edge in 1 second has to go a larger distance in 1 second. This edge has to come here for 1 gallon of water to flow through the narrow end. So it has to go through a larger distance in 1 second. Here it has to go through a smaller distance in 1 second. So this edge from here to here in 1 second has to go a smaller distance. Here it has to go a larger distance. So the speed, remember distance over time, the speed here is larger. The speed here is smaller, right? So whenever the speed, when a fluid flows through a narrow pipe, the speed of the fluid increases. So the fluid begins to flow faster. All right. So what does that mean? That means according to Archimedes, if the fluid goes faster, the velocity, if the velocity increases, the pressure here, and I'll explain why, the pressure here is less. Pressure is less. So smaller pressure. Here, because the fluid is going slower, the pressure is larger. Okay, the pressure is larger. So small speed, large pressure. Large speed, small pressure. Right? So once again, according to Archimedes, if the speed increases, the pressure decreases. Right? Now, I don't know if you have ever seen what happens in a river, right? When it narrows, the water really begins to flow really fast, right? People use that when they go, what is that, rafting, right? The rapids. You can see whenever the river narrows, the speed of the water increases, right? That's because the same amount of water has to go through, but because this has narrowed, it has to go faster to accommodate the amount of water that's going through, right? What about if you are in a river, right? Sometimes rivers can be deceptive, or lakes, right? Or rivers. Suppose this is the bottom of the river, right? What happens? And this is the water, right? Can you see here the water is flowing faster because it's narrow, right? And then it gets deep, so the width is increased. So here the speed of the water is larger. Here the speed of the water is much smaller, right? So depths, they have a saying, still waters run deep. Run deep, right? whenever things appear calm, right? If you're swimming, whenever things appear calm, right? Things are not flowing past you at high speed, right? It means that the depth, it's deeper. That's why, okay, the waters are still, right? It's deceptive. You think it's calm, but in reality, uh, it's really deep. That's because the water is not flowing as fast, right? So anytime a pipe narrows, the speed of the water increases, or the speed of the fluid increases. And what about the pressure? How is pressure related to that? Okay. So if I take, suppose you have this pipe. Let me use a different color for the pipe. So this is the pipe. Right? And let's say this is the amount of water, there's water going through here. So a plug of water that's going through. Okay. So this water is going through. Okay. Can you see the area here and the area on the other end are the same, right? There's water going through. Now, because it's narrowed, the speed here is larger than the speed here. Anytime it narrows, the speed gets larger. All right? So what does that mean? For it to speed up, can you see the pressure here or the force has to be larger for it to speed up, to accelerate, than the force here. The net force has to be larger. So if the force is larger, what is the pressure? Pressure is equal to force over area. Here, the force is larger. The area is the same. This area is the same as this. So the area is the same. So what do you get? Force divided by area, you get a larger pressure. So the pressure here, smaller speed, larger pressure. What about on the other end? Right? What is the pressure here? Pressure, here the force is smaller. The area is the same, the area of the water going through. That's the same size as that. So smaller force will give you a smaller pressure. So whenever the speed increases, the pressure decreases. Whenever the speed decreases, the pressure increases. You can use the same argument on the other side, right? You have okay. So this is the area, same area. Okay. Right? So what do you have? You have the force here. Now it has to slow down. So the force here has to be larger to slow it down. The force here is smaller. To slow it down, the force here has to be larger because once the thing broadens out, the speed decreases. Okay, the speed gets smaller. All right, and therefore the pressure here is going to be what? The pressure here, larger force, same area, will give you a larger pressure. So when the speed decreases, the pressure drops. Okay, so here to slow it down, you need a larger force and therefore a larger pressure. To speed it up, you need a larger pressure on this side. So the pressure here is larger. The pressure here is smaller. All right, so this is Archimedes' principle. Now, the applications of Archimedes' principle. The application of Archimedes' principle. One is, in a storm, right? What happens? This is the roof. right? In a hurricane, the winds that are going are very fast, right? So can you see the speed of the air here is larger? So if the speed is larger, what happens? The pressure here is smaller, right? Inside the house, I should have used a different color here, right? So this is the house. Inside the house, the air is not moving at all. So the pressure here is larger. The pressure outside, because the air is moving, larger speed, smaller pressure. Right? So what happens? Because the pressure here is larger than that, sometimes the roof comes off. Okay? The roof gets blown. Okay, so that's one example of Archimedes' principle. Other examples of Archimedes' principle are, if you take a ball, right? If you throw it, it takes this path. But if you spin it this way, right? If you spin it this way, it will drop quicker. Okay, and there's a reason for that. If you spin it the opposite way, spin it this way, then it will drop slower. It won't drop as quick. Okay, and this is based on Bernoulli's principle. So why is that? So let's try to understand that. Suppose you have a ball here, right? And you, baseball, right? You spin it this way. Now a baseball is rough, right? There is that rough part, right? On the seams, it's rough, right? So what happens when you spin it this way? As it goes forward, there is air that is rushing, right? So the air that is rushing, right? This air, because the rough part will grab this air and speed it up on this side. So the speed increases. What happens on the other side? The air, can you see the ball is turning this way? The air is coming that way. The rough part will hinder the speed. The speed here decreases. So on this end, it will pull the air and speed it up. On the other end, as it's spinning this way, right, the speed of the air will be shorter. And therefore, large speed, small pressure. Small speed, large pressure. Can you see the pressure here downwards is greater than the pressure upwards? And so what will the ball do? The ball, instead of going this way, will now drop quicker. Okay. Another example of this would be, suppose you're spinning it in the opposite direction. Right? You spin it in the opposite direction. You spin it this way. Right? In baseball. Or in golf, what do you do in golf? You chip it so that it begins spinning this way. Right? And it's moving forward. So now the air, can you see the air here? Because it's turning this way, it will pull the air and the speed of the air will increase. Whereas on the bottom, the air, because it's coming this way, they're opposing. This is going this way, the air is going that way, the speed will decrease. Larger speed means smaller pressure, right? The downward pressure is smaller. Smaller speed, larger pressure. So what happens as it goes forward, the pressure pushes it up. And so instead of going this way, right, this will go much further. So in golf, that's what you want, right? You want it to go further. So you spin it that way. You spin it that way, counterclockwise, right? So instead of going in this direction, it goes that way. So you get a larger distance from the spin. Now remember, in baseball, you have the seams. So you need some rough edges to do that, right? In golf balls, what do they do to the golf balls to make it rough? They put these small pock marks on it. So if you look at a golf ball that's produced now, it has a lot of these dimples. If you look at the old golf balls, somewhere in 1910, 100 years ago, they were smooth. They didn't have any dimples, right? Now they put dimples. They make it rough, right? So that the air can be dragged. And by Bernoulli's principle, if you speed up the air, the pressure will drop. If you decrease the speed of the air, the pressure will increase, right? So let's do a few problems. Again, guys, I'm still struggling trying to get labs, this thing, but I can't leave the house because I have to stay in the house. Normally, I would have gone to the college and done, whatever is needed. I have to stay in the house. I don't know if I told you, I did get the COVID virus. I was, so I went and tested, and eventually I didn't get, mine was a mild case, but I'm still supposed to stay in the house, and until, so I was tested a few days ago. I still have the virus. Hopefully in a few days, in a week's time, when I get tested again, hopefully everything will disappear. That's my hope, right? But
I hope you
so
get well.
yeah. So far, I had a mild fever, and I had started with a cough, okay, and other things like diarrhea and all, but most of them have gone away. And so, so I should, maybe in the next test, I'll be given an all clear signal. So, so uh, I'm stuck with this. So anyway, let's do a problem. Uh, if you go to page 260, right? Uh, let's see. Let's see if you can do. On page 259, see if you can do 67. Okay, page 259, 67. So a solid ball with a volume of 4 cubic meter, 0.4 cubic meters is made up of a material with a density of 3,000 kilograms per cubic meter. What is the mass of the ball? Okay, so see if you can do this. There is a solid ball, okay, that has a density of 0.4 cubic meters. So the density is 0.4 cubic meters, right? And I'm sorry, it has a volume of 0.4 cubic meters. What am I doing? This is the volume. And the density, okay, is 3,000 kilograms per cubic meters. Okay, so what is the mass? So how do you find the mass? Remember, density is equal to m over v, right? Density is equal to mass over volume. So how do you find the mass, right? If you cover this, it's density times volume. So what do you get? Density is 3,000 kilograms per cubic meter, and the volume is 0.4 cubic meters, right? So 3,000 times 0.4, you get 1,200. So this is 1,200 kilograms, right? Let's see if we can do on page 260. See if you can do, let's see here. See if you can do 76. It says two barometers are made up of water and mercury. If the mercury column is 30 inches tall, how tall is the water column? Okay, so two barometers. This is 76 on page 260. So if the mercury column is 30 inches tall, right, and we are told it is 14.7 pounds per cubic inch, right?
Didn't you say every 10 inches is about like 7 something?
So let's, so
So 7 milligrams of mercury.
yeah, so 700 and or 776 centimeters, which is 760 millimeters, okay, is yeah, that's equal to 10 meters of water. 10 meters of water. 76 centimeters of mercury, Hg, okay, which is 0.76 meters. Okay. Also, remember the conversion, 1 inch. So let's make this centimeters, 76 centimeters. 1 inch is 2.54 centimeters. Okay. So if I want to convert 76 centimeters into inches, I want to get rid of centimeters, I want inches, and one inch is 2.54 centimeters. So centimeters and centimeters divide out. So if I take 76 and divide by 2.54, I get 29.92, or approximately 30 inches. Okay. So that is a 30 inches. So how much water would that be? That would be 30 inches tall. Okay. If the mercury column is 30 inches tall, how tall would the water column be? It would be 10 meters, right? Tall, because this is about 30 inches. So the answer would be 10 meters tall. If it was 15 inches, this would be 5 meters, and the outside pressure would be 50, right? 50,000 pascals, or 7.35. So this 30 inches of mercury is 10 meters of water. Let's see you try. So see if you can do 81. See if you can do 81. Guys, did I do, I just want to ask a question. Did I do 70, did I do chapter 8, chapter 9?
No, you just did chapter 8.
I did chapter 8, right?
Yes.
Okay, all right. Not 9. So see if you can do 81. So it says a 500 grams wooden block is lowered carefully into a completely full beaker of water and floats. What is the weight of the water in Newton that spills out of the beaker? Right? So you have a beaker here, and it is filled completely with water. Okay, and you put in a 500 gram wooden block. It's carefully lowered. Okay, what is the weight of the water in Newton that spills out of the beaker? So the moment you put this wooden block that has a mass of 500 grams, okay, so if I put this wooden block, it floats, right? And this beaker, which was full before, now the water that spills out, this amount of water spills out, right? So how much water is that? Because the mass is 500, right? The weight is approximately what? 500 times 10. This mass is 500. What's the mass in kilograms, right? 500 grams. I want to get rid of grams, and I want kilograms, and 1 kilogram is 1,000 grams. So 500 divided by 1,000 is 0.5 kilograms. So this is 0.5 kilograms, right? And what is the weight? Weight is mass times gravity, which is what? 0.5 kilograms times approximately 10 meters per second squared, which is what? 5 newtons. So this has a weight of 5 newtons, right? According to Archimedes' principle, the amount of water pushed aside would be how much? Anyone? For it to float, how much water would have to be pushed aside? 5 newtons of water would have to be pushed aside, right? Then the downward force is 5 newtons and the upward force is 5 newtons. And so it balances out, right? So the question is, what is the weight of the water in newtons that spills out of the beaker? The weight of the water that spills out of the beaker is 5 newtons, right? Okay, so for your homework, okay, we are going to do on page 259.